Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello, everyone. I'm going to stop screen sharing. That's right. So if you're joining me live, welcome. It's just me today. My colleague Alex is out, but thank you for joining me. This is another edition of Ask Us Anything About Electrochemistry 2024 style, I suppose. This is the first one of the new year. So if you are with... There we go. Get rid of the video playing in my ears. If you're with me, welcome. Happy New Year. And I hope you did have a good holiday season. Just a few notes off the top before I get started. So this is, as you can see from the title, a live stream that my colleague Alex Paroff and I tend to do. I'm Dr. Neil Spinner. I probably should introduce myself as well. Alex usually does the intro, so I'm not good at this part, but I'll do my best. So this is Ask Us Anything About Electrochemistry, as the title implies. That's where you, as a researcher, graduate student, postdoc, professor, undergraduate, someone trudging through the woods, looking on your phone at some strange YouTube video, whoever you are, if you have questions about electrochemistry, this is the place to ask, or about life in general, I suppose, but specifically electrochemistry. Happy to answer those. And I work at a company called Pine Research, and we started this live stream last year as a means to answer these kinds of questions, because we tend to get a lot of questions through email, through phone calls. I do webinars and all kinds of different traveling trade shows and things of that nature, and we get a lot of questions. And so we wanted to find a way to provide kind of an outlet. You could think of this, if you're perhaps in undergraduate or graduate school, something like an office hours where your professor will, be in his office to answer questions you have about the exam or about your research for a couple hour period of time each week. So that's what we're trying to do with this event for you, what we do each Friday. So a couple of things. Again, I'm using a platform called Restream, simulcasting it on Twitter, X, and on YouTube. And so there is a 20 or so second delay, usually between when I'm saying these words and when you will hear them. So bear with me if for example, if you ask a question, there may be up to a half a minute to a minute delay before I'm able to read it and you'll hear me reading it, and then I can start to answer it. But I will certainly do my best to cut down on that delay time as much as possible. If you are a member of our YouTube channel, thank you. Want to give a shout out to our members. That's where a lot of the previous webinars that I've given can be found in their entirety. So you can watch some of those webinars I've given. I gave one on RRDE and rotating disc electrode Levich analyses just before the holiday break. And thank you for anybody who joined me then. And those recordings are also on our YouTube channel, in addition to my 5-part EIS webinar series and a couple others that I had done in the past few years. So a few other things, and then I will get started with answering some questions. The first is I just want to say off the top that electrochemistry is really hard. So the point of this live stream and this event is to be an outlet for you to ask questions that even you might feel stupid or think are dumb or think are too easy, or you're maybe afraid to ask your professor or your advisor, things of that nature. I want this to be a kind of electrochemistry a place where you can ask any question, even if you think it's silly. We're not going to judge any questions, and I'll certainly do my best to answer. And I might get things wrong. I'm going to do my best. I'm a PhD trained electrochemist, but I certainly don't know everything. So I will do my best to answer those. And usually my esteemed colleague Alex is here to also answer, because we both come from slightly different backgrounds and have different expertises. And so there's things that he just does way better than I do. And so anyway, all of that being said, I'll do my best to answer your questions, but I don't want people to feel intimidated if there's a question that you think, oh, well, I feel uncomfortable asking that, or I've always wanted to know this, but it feels, I don't want people to laugh at me or something. There's no judgment in that regard, certainly here. This live stream, I'm going to aim for about 1 to 2 hours. It depends how many questions there are. I can be here and sort of, again, just have this office hours kind of feel to it. So if you have questions, type them anytime into the chat and I'll get to them as quickly as I can. And then the last thing that I'll mention, just as far as those questions go, from our experience now, we've been doing these for almost a year. There are two extremes of electrochemistry type questions, neither of which are really useful. And so as you're formulating a question, or if you're thinking about what you would want to ask, I would suggest that you avoid one of these two extremes. And so the first extreme is something like, what is electrochemistry? It's way too broad, right? Like, how do I do circuit fitting in EIS? Like, those questions are so broad, they would take a semester of a course to answer, right? It's too general, right? So those are hard to answer in any kind of concise fashion in a short live stream, right? So I would discourage you from asking those. The other kinds of questions are all the way on the other end, which are to say, you might ask, what is the mechanism of the third electron transfer of manganese to spinel oxide when it is interacting with a 0.25 molar solution of perchloric acid? Like, that is so utterly specific that unless I happened to do my PhD on that exact topic, I probably can't help you. So in other words, if you have a question, my suggestion to you, as far as getting the most out of my ability to answer it, frankly, is to ask something in between those two crazy extremes, is my suggestion and my hope for you, that you perhaps have questions that line up somewhere between those two things. Okay. So the first question that I do want to get to, there was one that was typed, I think, earlier this morning. So I've kept it here in preparation. And it has actually a little bit of an illustration of that point I just made. So this was by a YouTube person who has the name Chemistry Learned by Heart. And they have asked, what mechanisms are used in electric cell and electrocatalyst? So I'm not trying to pass any judgment here, but just objectively, that first part is quite broad, right? What mechanism are used, like, in electrocatalysts? So many, right? That you'd have to be more specific, which is why I like this question because the next part of it is specific, and I can talk about this. So it kindly explain the 4 types of OER mechanisms. So this is kind of a great question to illustrate this point, right? If you just say, what are mechanisms in electrochemistry? That's very, very general and hard to answer. But what are the mechanisms of the OER, which is the oxygen evolution reaction? Well, I can talk about that a little bit. So let me try to answer that. And then I will get to the live questions. I do see there are a few. So I will try not to take too long, I promise. But I did want to answer this question because this one was posed chronologically first, actually. So, okay, let me just make sure. It's just me here today, so I have to, whoop, that's not what I want. Okay, so you see my screen, you can hopefully still hear me. Somebody, if you can't hear me or something, or you can't hear me, it'd be nice to get verification. Usually I have Alex here to like help me make sure I'm not doing something ridiculous. Okay, so what I'm going to do, so the oxygen evolution reaction, OER, right? That stands for oxygen, just shorthanding here, evolution reaction. There are 2 general types, one in acid and one in base, one in alkaline. I'm going to talk about the one in acid just for simplicity. There's 2 sort of answers to this question, the mechanism. But the oxygen evolution reaction in acidic environments is 2 water goes to O2 plus 4 electrons and 4 protons. Okay, it's the opposite of the oxygen reduction reaction, essentially, for those who may be studying fuel cells or things like that. So that's the oxygen evolution reaction. Now, the general consensus, which is the point of this question, is that there's a 4-step kind of a process. Apparently, again, I think this is somewhat of a theory. I don't know how many, I don't know what you say, like in situ or observational proof or evidence of this is, but it's sort of a, I guess, accepted, if you will, observation of this in the literature. And so it's essentially 4 steps of releasing this. Like it's 4 steps, and each of the steps releases 1 electron and 1 proton. Okay, so essentially what you have first is, maybe I'll do these in different colors. Maybe that'll kind of help here. So like step 1, and this is the electrode surface, by the way. I just drew electrode surface. So it's maybe hopefully a little easier here. So the first is that 1 water molecule goes to the surface, okay, and you get an OH like adsorbed on the surface. This is keep in mind, this is like a mechanism thing. So sometimes you get weird stuff, like you get like sometimes it'll be like OH, you'll see like ADS for adsorbed. It's not hydroxide, it's not OH minus, it's just OH, which kind of doesn't feel like it makes sense if you're thinking about it. So it's like adsorbed to the surface, and off comes an electron and a proton. So you see that essentially the charge is balanced, right? 1 minus 1 plus is 0, right? This is still 0, water is 0. It's like that's why it's not OH minus. So apologies if this is a little confusing, but basically it's the actual stoichiometry of this is 1 water, H2O, for step 1 goes to OH. Again, you might call it adsorbed, plus 1 electron plus 1 proton. Okay. Step 2 is where that OH breaks apart. Okay, so let's do step 2. The OH breaks apart to another proton and another electron. Okay. Or I should say the H goes away, the O stays on. So like the H basically disappears, right? Or desorbs, whatever you think using the right words here, right? But okay, so step 2 is again this OH adsorbed, so to speak, here becomes an O. And again, this is not like O negative. It's not oxygen. It's like elemental oxygen. It's a mechanistic thing. It's a little tricky to conceptualize because it kind of feels like, well, you just have one oxygen atom. It has no charge to it or anything like that. It's a bit odd, to be perfectly honest, to conceptualize. But this is sort of the agreed upon mechanism, if you will. The next step 3, okay, we have another water molecule that makes its way over to the adsorbed oxygen. So you can see I've got just from the step 1 and then step 3 is where the 2 waters come into play, right? So this water molecule goes to the adsorbed O. We have our absorbed O still on the surface, and that we get another E and proton that come away. And what's left on the surface is OOH. So this, like, sometimes we call it oxyhydroxide. And that's the adsorbed whatever species that's left. So step 3, we have this O adsorbed plus a water molecule. Okay. And that gives OOH is what's sort of left adsorbed, right? So we have 2 O's and 1 H, 2 O's, 1 H. The other H goes away to be the third of the 4 electrons and protons. And then finally, the last step, and then I promise I'll get to other questions, as I see there are some. Step 4, I'm sorry that I've not done a good job leaving myself enough room, is the OOH sort of breaks apart, okay? The OOH, again, we're going to leave, we're going to lose and get the last proton and electron, and what's left is just 2 oxygens. And so that's where our oxygen comes from. That's where the evolved oxygen comes from, is in this step 4. So OOH adsorbed, that basically breaks apart into our oxygen gas. You know, I could put G for gas that evolves away. That's the oxygen evolution, plus the last proton, electron in the last proton. So that is the, acidic 4-step OER mechanism. That's, again, generally accepted. It's a bit odd to think about the adsorption thing, but this is how you do it, or how it's generally described. Okay. And there's a similar but a different mechanism for the alkaline one. It's a little different. It starts with hydroxides being adsorbed to the surface. There's some other steps, of course, similar kinds of things. But yeah, and then you'll, the analogous situation being mechanisms for oxygen reduction reaction. It's sort of a backwards thing, and that's a whole crazy thing. If you try to find a search in the literature for oxygen reduction reaction mechanisms, you'll find like 50-step process. It gets kind of crazy. Some people have really interesting papers and publications and what have you with different mechanisms for the oxygen reduction reaction. All kinds of different electrochemical mechanisms. Anyway, all that is to say that it gets complicated, but that's hopefully a relatively quick answer to that question. And I will show. There's one paper that I guess I can recommend here, from which this is laid out pretty well too. I'm just going to share this paper to give some attribution. Let me find it. It's right here. So this is by a research group it looks like from the Netherlands. So you see this is the Journal of Physics Energy. It's like it's from 2021. So there's Chu Liang and in this group. And so this paper is quite concise. It shows those mechanisms. You see that for the adsorbed species, they kind of have this asterisk. It's a bit of a different nomenclature. They show it for the acidic reaction. They talk about Gibbs free energy, and then for the alkaline, they show it down here. The 4-step is still slightly different, but similar phenomenon. Anyway, just a quick little plug for it's a useful paper. Shows that mechanism. Okay, so this next question's from Mawish. Says, "Hi, can you tell me about the potential of electrochemical water splitting?" So, well, I suppose conveniently, I just inadvertently did some of that. So the oxygen evolution reaction is like half of the water splitting reaction, right? The water splitting consists of evolving hydrogen or oxygen. Um, you know, I guess in the absence of more specificity to your question, you want to tell about the potential of water splitting. I mean, very generally speaking, highly positive potentials are where the oxygen evolution reaction occur, and that's the one I just showed. Right, I just showed it in my little description of the mechanism. But water in acid media, let's say again, it's different for alkaline, but in acid media, water splits into oxygen and then protons and electrons, and that's an oxidation reaction that usually happens. Again, it depends on the environment, the pH of your system, your solution. It depends on your reference electrode. Depends on a lot of things. But let's just say like 1 to 1.5 volts, generally, give or take, is where you'll start seeing, like if you're doing like a cyclic voltammogram, you'll start sweeping positively, and then like the current will start shooting up. That's the oxygen evolution reaction. That's like the splitting of water to produce oxygen. And on the other hand, the other half of that is the hydrogen evolution reaction, right? The HER. And it's just a analogous thing that happens at negative potentials. So again, it depends on all of those factors. I said pH and your reference electrode and your system and all of that kind of stuff. But let's just say lower than 0, -1, -0.5, it depends. But you'll start scanning negatively, and the current will drop into a more reduction uh, uh, currents, and that is where you start evolving hydrogen, a gas, right? Right. So, um, so if you think about water splitting combined, right, you can think, well, how can I evolve hydrogen and oxygen at the same time, right? Consider like the simplest example of like a 2 electrode system. If I just put 2 like platinum wires into water, or like some solution with salt in it, whatever I'm applying at the positive electrode or the negative, whatever, on one electrode has the equal and opposite at the other one. So if I'm applying positive 2 volts and I'm just generating oxygen over there, well, the other electrode will have negative 2 volts, and that'll be generating hydrogen. And so the most general sort of conclusion of this that I'll say, and then I'll move on to the next question, is you could think of um, like electrolysis devices and water, devices that produce hydrogen or oxygen for water splitting. You can think of them kind of like that. Now, it's in reality, it's obviously quite a bit more complex, and the structure of these devices is more intricate and everything like that. But you can kind of think of it like it's just a big potentiostat in a big vat of water with some salt, and they're just dumping 2 electrodes in it and zapping them. And on one side, you have a positive potential, and the oxygen is collected, and that's used for whatever you're using oxygen for. And the other side has the corresponding negative potential, and that's zapping the water and producing hydrogen. And then the hydrogen gas is collected to do whatever you're doing with hydrogen. So, so that's, I don't know, hopefully a decent overview of water splitting, right? Hydrogen and oxygen evolution reactions. Okay, this is a new question from Alex. It says, "Hello, please explain the fundamental difference between CV and LSV. Why do researchers sometimes use LSV instead of CV? I'm studying HOR. Can I measure CV, cut out half, and say that there's LSV?" So HOR, why am I blanking? I'm gonna hydrogen evolution. Wait, HOR is not hydrogen evolution, is it? Hydrogen oxidation. Can you clarify what HOR is? I'm having a senior moment, and I'm not thinking. But I will answer the other part of your question. And the general answer is, can you measure CV, cut out half, and say it's LSV? Yes, you can. So let me draw a few things while I wait. Maybe you can just. I feel like I'm missing HOR. I can't like put my, it's like it's on the tip of my tongue, and I can't remember hydrogen. It's not hydrogen evolution. It's a hydrogen oxidation. I guess it must be hydrogen oxidation. trying to do this little drawing here for you. Hydrogen oxidation. Okay, yeah, that's then that was what I thought. Okay. Let's see, make sure I'm sharing my screen. I am. Let me okay. So yes, in short, you can certainly do a CV scan back and forth, and then call it, and take half of it, and that's your scan. Often things like if you're studying hydrogen oxidation, oxygen reduction, whatever, oftentimes you're looking at what's called a polarization curve, which is it's an LSV, right? Basically, if you're talking about a device like a fuel cell, an electrolytic cell, those tend to be characterized by polarization curves, which is basically a CV with the axes reversed. So a CV has current over here, it has voltage over here, and then if you're doing hydrogen oxidation reaction, a lot of times, I would say one problem or tricky thing about hydrogen oxidation is that it can be messy, it can be noisy because there's hydrogen gas. Hydrogen gas elutes really fast. It's hard to sometimes keep hydrogen gas in your solution. And then because it's gas, it breaks up the electrode electrolyte interface quite often. It makes for some noisy data sometimes. So I just wanted to say that if you're facing that, I understand that problem, let's just say, right? Let's just pretend it's clean though. Sorry, back to the point about polarization curves. A polarization curve is usually something like this where they're just reversed, right? And so if this is like your open circuit, as you drop your, I don't know, it might have something like that. As you drop the potential, you start getting more current out of it. And that's just a reverse presentation of cyclical telemetry or LSV data. Okay, so this is like CV or LSV. This is polarization curve, just for what it's worth. Now, as far as the CV versus LSV is concerned, sometimes what people do, I should make sure that you can see this. Let me get the question away. I know I'm drawing below the question, so okay. Sometimes what people will do, for example, to do a CV is to look for what's called hysteresis, right? So if you scan up and then you scan back, sometimes it won't trace entirely on itself, right? I mean, it almost never will exactly. I'm not talking about, I probably shouldn't even really be talking about this region. It's more like when you do oxygen reduction reaction under rotation, for example, you get this sort of S-shaped curve. And then in theory, when you go back, it should be perfectly tracing on itself. But a lot of times what you get is it's perfectly tracing for a bit, and then the S curve has a bit of a hysteresis, and then it comes back. And hysteresis is just hysteresis. Okay, that's just the sort of this gap between the forward and reverse scans. Okay. I'll just be perfectly honest. It's been a while. I did this like when I was in graduate school. There's a lot of, to my recollection and perhaps somewhat experience with this, there is some like unknown. It seems to be like one of these things. Not people aren't 100% sure. I don't know if it's like a surface cleaning thing, or it's some surface state of some kind like that causes. I remember I did a little bit of this, like when I got into graduate school, I'm learning the ropes, so to speak. And I would do like oxygen reduction reaction on like a platinum electrode to just sort of learn electrochemistry, to learn the basics of it and this and that. And I learned a lot of this kind of stuff. How do you say about the oxygen reduction and then the hysteresis. So I learned some of the common knowledge or stuff. And to be perfectly honest, I don't remember 100% of like the explanations for it. Sometimes what people do, for example, or they used to do, I don't know if they still do, with like oxygen reduction reaction. And again, this might be applicable to something like HOR as well for you. I'm just talking about what I sort of have experience with, is that they'll scan, backwards and then forward. And then it's like, and then they'll get rid of this one and just use the second one, or, a second scan. And there's a reason for that, because sometimes, or vice versa. Right. And some of that is because the better, onset potential is obtained in one of the scans, which is to say you want a lower onset potential because that's like a better over potential. It's a stronger driving force. It means your catalyst is doing better. So sometimes you'll do a CV on purpose and then pick whichever one, right, half of your CV, if you're doing back and forth, is best. And there's reason for that too, because I guess you make the argument about its surface is more pristine or something. Again, I'm sort of hazy on the exact details. I don't remember them 100%, to be perfectly honest. But the point is that you can certainly do that to sort of help yourself find the half LSV that is best for your data or most conducive, I think. So something of that nature. And I know I glossed over the first part of your question, to be actually, now that I'm realizing, but I hope that actually made it somewhat evident. What I'm talking about is that the fundamental difference between CV and LSV, there isn't one insofar as the experiment is concerned. You're scanning the potential linearly over time. LSV is just where you go one direction only. You start here, you go here, you're done. Cyclic voltammetry is when you do the same thing, but you go back or back and forth. So, LSV, if we're talking about potential versus time, LSV is one direction you go, or you go down, whatever. So you either go up or you go down, but you start somewhere and you end somewhere. That's it. Whereas CV is there and back, or there and back, and then you go back and forth, hence the cyclic part, right? You could go down first, you can any bit of that, but you're going back and forth with your potential. And so it's just a CV is just a series of LSVs. That's really the only difference, right? And then I hope I've answered to a little bit of a degree some of why people do that. And maybe, again, if you're seeing some of this hysteresis or something like that, and then sometimes just doing CV for a while and then picking one that is cleanest. If you just do one LSV and it's not that clean, you have to do it again and again. And so it's like, what's the difference between doing a bunch of LSVs in a row or just doing a CV and waiting for it to sort of stabilize or clean itself, get the surface to be relatively clean? There isn't much difference. So sometimes you can just do CV and until your data looks reasonable, I suppose. That's also sometimes an acceptable thing to do. So let me check. As I said, we are on Twitter. I don't think there's any questions on or X Twitter here. So, but I am trying to monitor that at the same time if there are people that have questions on Twitter. Supposedly Restream, which is the service the streaming platform I'm using, has chat or comments from X that come here. I haven't seen that happen yet. So if it does, I guess I'll find out later. But if you are on X or Twitter, you can type a post or a comment there, and I'll try to find it, and then try to answer it if I can. But it might also be easy to come to YouTube and type the question in YouTube, as I think that is the one that's easiest for me. Okay, so Dooley's is here and says, maybe you've answered this question before, but if not, can you explain how to use a Levich plot to estimate the number of electrons transferred to an organic molecule in a non-aqueous, that's a continuation of the question, in a non-aqueous system? Also, can it be determined if the number of electrons transferred is an EE-type mechanism? Okay. So let me answer your question first by pulling up the Levich equation, for those who aren't perhaps familiar with it. I did this in a webinar, actually, again, not that long ago. So I can pull up some of my slides from my RRDE webinar. Let me get that here and then just bring it up for reference in context. Let's see, here's Here's my webinar slide. So let me get to the Levich equation. Okay, Levich analysis. So this is the Levich equation. All right. Now, fundamentally, based on the Levich equation, in theory, the answer is yes. Right, because you have n, the number of electrons in the Levich equation, as you can see, right? So, again, in theory, you could imagine yourself with like a rotating experiment. If you're able to get a limiting current, right, IL, and let's say Faraday is constant. You know the area of your electrode. Let's say you know everything else. Let's say you have an estimate for the diffusion coefficient already, because again, normally, as I've said with Levich analysis before, is that it's diffusion limited process, right? It's an equation that describes the process at a rotating electrode that is diffusion limited. Okay. Part of the issue with this fundamentally, as I said, fundamentally and theoretically, the answer is yes, because n is part of this, equation. But it's tricky because this is not a equation that describes that's describing kinetics at all, right? And the number of electrons transferred is usually a kinetics, kind of evaluation, right, of your system. So I have some hesitation about wanting to use something like the Levich equation for that purpose. But in theory, and there's other equations like isn't the Randall's subject equation, for example, has, most of these equations, most, just pulling it up as well to have as a reference here, have an n in them, like that. Most electrochemical equations have a number of electron transfers. So in theory, if you know all the other parts of it, right, omega is the rotation rate, c is the concentration, the kinematic viscosity, and you have an estimate for the diffusion coefficient, you can plug these in and estimate the number of electrons transferred. So that's the first thing. But again, I sort of don't generally recommend it. And the most common thing that people do is that instead, if you have a rotating experiment, is that you go to the Katecky-Levich analysis and then to the Tafel analysis, because usually from the Tafel slope is where people really extract a measure of n, is what it is, because it's, in theory, if done properly, it's purely kinetic information. Now, the second part of your question is where it really does get hairy, for lack of a very nice, elegant word here. So if you have an EE reaction, right, that's like two electrochemical reactions in a row. This is actually one of those things I feel like I talk about relatively frequently. It's like, it's like one of my, Alex always teases me, it's like one of my triggering things, people using the Tafel slope and the Tafel analysis like improperly. Many electrochemists I see that get a LSV or a cyclic voltammogram or something, and they just immediately make a Tafel plot out of it. And it's like, that Tafel plot means nothing. It means nothing. Tafel plot assumes the current must be kinetic current and not tainted by any other processes. And so when you're doing that, you're making a leap of assumption. And the other part of the assumptions that are built in as well are things like perfect irreversibility and usually one electron. So there's this very interesting and paradoxical kind of assumption that is built into these analyses that's like immediately violated when we do the kind of thing that you're talking about, which I don't say that to say like you shouldn't do this, because this is like common practice. It's an odd paradox, but for the most part, these kinds of analyses assume one electron transfer, like one electron. And, Alex has talked about this too. I think in some of our previous, live streams, essentially that like one of the electron transfer steps or whatever is going to be the like rate limiting one. So a lot of times with these analyses, you're sort of lumping them all together and saying, oh, well, I have 3 electrons transferred. And it's like, you're sort of breaking the assumptions of using these analyses and these equations in the first place. So I always just want to mention that because it's like, if you're doing these analyses, you want to basically have that as a thing to write about in your discussion section of your paper, or to talk about in your presentation, or just to have that knowledge, so that, when a reviewer or someone says, well, what do you think about this number? Is that accurate? You can just sort of acknowledge, like, well, we know there's some inaccuracy to this analysis fundamentally, just to be fair, because if there's an EE mechanism, for example, if the first E reaction has 1 electron and the second one has 2, well, I can do this Tafel analysis, or, the Levich equation, like you suggested, plug in some numbers, and maybe I get close to 3 electrons, or maybe I don't, whatever, right? And you might say, well, that's the combination of the 2 reactions, but there's just some assumptions being made there. And so it's sort of like, if you don't get exactly the number of electrons transferred you, I don't know, think or hope or expect, probably it's because there's baked in assumptions that are being violated, so to speak, and you just have to be cautious about using these. I don't like to, I don't know, be so militant about it and be like, you should never do this, because like it's been done for so long. It's always, people use like the most common one probably for Tafel analysis is that people do oxygen reduction reaction. And oxygen reduction reaction is, when it's working great and your electrocatalyst is good, are is a 4 electron process, and then the oxygen reduction reaction that is undesired, that produces peroxide, is a 2 electron process. So what people often do when they're studying like novel materials for oxygen reduction reaction is they do a RRDE experiment, and they calculate the number of electrons transferred, and they also detect peroxide on the ring of their RRDE maybe. But they do this to see, well, if I get N is 4, well, that's great. I've got a really good, whatever. But if I get 2, it's like absolutely terrible, and peroxide is going to poison your catalyst and be bad. And then anything in between means I have like some, 80% of it is going through the 4 electron pathway and 20% is going through the 2 electron. So you do those kinds of games. But like, as I said, it's always like, okay, let's just be cautious here, because maybe that sheds insight into your mechanism, but also maybe there's just some issues because you're using an equation to lump multiple electron transfer steps all together when it really only assumes 1. So anyway, I'm going to stop ranting about that, but that's the long and short of that. I hope, Dooley's, that answers the question well enough. If you have other questions, please feel free to comment again if you need some clarification. But I hope that's a reasonable answer for you. Let's see. Next was a question from El Mehdi. Says, is there a trick to have reproducible signals when using modified electrodes? So like a catalyst ink dropped on a substrate. Well, there's a lot of tricks for that. Unfortunately, a lot of them are like, they fall under the category of practice makes perfect, or practice makes proficient, or like, and honestly, it's really more like arts and crafts, right? I'll talk a little about it, I guess. It's a hard thing this is also somewhat of a general kind of a thing, but it's also it's a specific, electrochemistry practice, right? And it's a very, very common one. So like, I can talk a little more easily about, like, if your substrate is a rotating electrode, right? You have something like a glassy carbon disc here. So this is, glassy carbon. So I'm just sort of coloring it in a little bit here, just for your so you understand. And this would be like Teflon, PTFE, shroud. Okay. And then this is, this is some electrode. So if you have something like this, for example, making your film on it is a multi-step process. It's like you have a beaker with some of your suspension and your particles. You sonicate it, or you mix it. It has to get mixed up, and then you get a pipette to get a small droplet out, right? And then you put that droplet onto the surface, and then you dry it so that when it's dry, it makes a film on the surface. So this is like, there's other ways to do this. It depends if your substrate is like carbon cloth, or I don't know. There's a million different ways you can do something like this, right? But it's basically a similar phenomenon where you have like a suspension of your stuff, and you're putting some fluid onto the substrate, drying it, dries and makes a film. So for example, some of the things that will help consistency are making sure you know every bit of those steps as accurately as you can. So what do I mean by that? I mean that you want to know exactly how many milligrams per milliliter of your catalyst are in this solution. Make sure you mass it and take the volume very, very carefully, very intricately, so you know what the loading is, so that when you take 20 microliter drop and you put it onto your substrate, or you take a milliliter, whatever the number is, right? You can multiply to figure out exactly, I have X milligrams of my catalyst present, right? So sometimes what you might be doing is if you're a little sloppy or not calculating all that carefully, you'll have an unknown amount of active material that you're depositing each time, and that you're in your search for reproducibility and consistency, that can impact it for sure. So there's that, just sort of knowing your numbers, knowing your values, being really sure about them. When it comes to the deposition itself, you want to make sure that all of the droplet is contained on your substrate, right? If the droplet starts to spread over here, well, then it's going to dry, and then some of your active material is now over here on the substrate. Frowning face. That's bad, because that's not part of your electrode now, right? So that's another way for you to have an unknown loading, an unknown amount of active material. It's not on the substrate itself. So you have to be very precise. This is what I mean by arts and crafts, because like all of these things I'm talking about is like stuff you're doing very it's laboratory work. It's not data analysis, right? This is like making sure you're really steady with your pipette, and your mixing is good, and your ability to center the droplet on the substrate is good, or spray it, properly, something like that. Sometimes it's like a spraying, and then you dry it and mass it to get the loading. There's like, as I said, there's a lot of ways to that people do substrate film kinds of preparation. But having all of those numbers and having all of that amount there will help reproducibility. The only other thing that I'll say, again, this is somewhat of a general question, and again, if you want to comment more specifically on like, I don't know, your type of substrate film that you're working on. The other thing I will say, as far as reproducibility and trying to help that, is that the interaction between the substrate and the film matters as well, and the adhesion, right? And so sometimes reproducibility happens because the interaction between like the substrate and the film is not so good, right? It's like if it's starting to loosen up and fly off, right, you're getting this like desorption, flaking off. It depends on what form it is, but often, for example, in the process that I just described, people will either add to this blue droplet or add a second step of like a suspension of something that acts like a binder or a glue, like a Nafion suspension or some other ionomer. And the reason for that is that it's sticky. So it's like what you actually have, in some manner of speaking, is your substrate. And then you have, this is like way oversimplified, right? Of course, but you have your substrate and then your film, and then you have like either mixed in or like around it, you have like some kind of glue, and that keeps it in place. And then obviously you need to make sure that like solution can like penetrate the Nafion, which Nafion's good at that if you're doing, acidic kinds of things. I'm glossing over a lot of details, I know, because I'm trying to answer your question relatively quickly, and it's pretty general. But the point is that this adhesion, adding a little bit of like Nafion suspension, adding some ionomer, adding something that will help the adhesion between substrate and film, very often irreproducibilities and a lack of consistency in your data comes because the film, if the film is no longer there or falling off to any degree, well, then it's the same thing as not knowing your numbers all that well. You don't know what your loading is. You don't actually know what your loading is. And so the amount of current you're going to get is going to keep changing. Not enough of the film is there. Well, you're not going to get the kinds of curves that you're looking for. Right. So all of those things are going to impact the data that you have. So I hope that's a relatively quick overview of these kinds of processes. As I said, the process of doing a substrate in a film is pretty varied, right? And there's a lot of ways that it's done, and so there you go. I hope that's a decent overview. There's mostly the work on you to practice those steps until you're really solid on them. I suppose that's the best advice. Okay, let's see. So I think this looks like a general question. I need help with transfer coefficients. I'm not sure. Do you mean is like a charge transfer coefficient? I'm not 100. Do you mean like let me so like in the Butler-Volmer, hang on, I have the presentation up here. I think in the Butler-Volmer equation, let me just try to, if you're here, I'm sorry, I'm all over the place here. Anisha, maybe you can clarify a little bit. Are you referring to, where is it? Yeah. For example, in the Butler-Volmer equation, where am I? This one. So this right here, alpha in the Butler-Volmer equation is called the transfer coefficient. It's a symmetry factor, which describes the energy barrier, how symmetrical it is between the anodic and the cathodic half reactions of a directions of a redox process. I assume that's what you mean, but I don't know if you're referring to something else. Or for something else is coming to mind, like I can't like the amount of charge carried by a species. What is that word? I can't remember it. I wish Alex were here. Anyway, if you can clarify a little bit for me, I would appreciate it, because I'm not 100% sure if that's what you're referring to, is like the alpha, like symmetry transfer coefficient, that or it's something else. I don't want to dive into a discussion of something that isn't really relevant or what you're asking for. So I'll just try to monitor if you have a clarification. Let's see. There's a question from Rasmi saying, okay, so for EIS of a polymer coated metal with 2 time constants, which circuit to choose between ladder circuit or series circuit, and how to justify it? Okay, so I can answer this one. Again, I have a presentation from a webinar I can pull up EIS. Let's see. I think it's in this one. I can try to give you a reasonable answer to this question. The short answer is it depends on whether your substrate your film fully covers the substrate or not. Okay, so let me share. So you have a polymer, you have a metal, which is your substrate, and you have a polymer on top of it, which is the coating. So the substrate is the metal, the film is the polymer, and you have two time constants, which means you have two semicircles, so to speak, right? Let me share. This is from the second part of my 5-part webinar series. Okay, so by two time constants, you probably see two semicircles like this, and you're basically wondering whether you have, what are the words you used, a ladder or interesting terms. I haven't really heard these terms for ladder or series. Okay, so I use the terms embedded in series. So this is the series model, right? And then perhaps what you're calling a ladder is something like this, where they're sort of on top of each other. Yeah, I call it embedded. I mean, terminology is irrelevant in some sense. Okay. The determining factor is whether this film fully covers the surface or the substrate is partially exposed. So you see the difference between these, like, I'm not going to do the whole animation here. The point is that it's similar to that whole process I just talked about. Dropping a bit of your catalyst onto a glassy carbon, right? If you drop it on glassy carbon, you drop your film and it's like fully covering it. Okay. Then it's like what I have. Let me actually pull up another presentation because I have a good illustration of that as well. But what you have when you drop it and it's fully covered is you have like two distinct interfaces. Okay. I'm going to pull up a different one because this might also help drive the point home. Give me a half a second to find it. So I'm going to share a different presentation now. And I hope this will be a decent answer to what I'm talking about. So, okay, so look on the left here. This is the situation of a series. Okay, my substrate's fully covering my film. So I have two distinct interfaces, which is probably leading to your two time constants. This is for you, the substrate, this is your metal film, this is your polymer, and then you have an electrolyte. And so the two, in this case, if I'm not porous at all, my polymer's solid, there's no interaction between an electrolyte and the underlying substrate, then I have two in series. That's like the progression that you have here. On the other hand, I could have something like the one over here. I know it doesn't look like the other model on the other that I just showed, but this is essentially what it is. So if I have some porous amount, so I have my film and I have my substrate, but I have electrolyte that can touch either the film or the substrate, then what I end up with is this sort of you called it a ladder model, something like that. But I basically, it's not exactly true. So I'm gonna gloss over it just a little bit. So apologies. You can kind of think of it like, let me do a thing here. The ladder or the embedded model, okay, is, I'm going to just do a thing so I don't have to share a different presentation entirely. So this is the slide that I was just showing you in my other webinar. This model here, you kind of think of this as, this is the first time constant, if you will, is the embedded, the interaction between the electrolyte and the substrate. And the second one is the interaction between the electrolyte and the film. Okay. So whereas the series model is, the first one is the interface between substrate and film. And the second one is just film electrolyte. So the difference is between whether the substrate is, the time constant is related to the substrate and the film, or the substrate and the electrolyte. Now, oftentimes you can differentiate this if you have a system where, for example, as you change the potential and you change some other conditions electrochemically, the first time constant or semicircle does not change, that is probably an indication that it's this one. The substrate in the film is the first one. Because if you change the potential, I would expect everything to change except things that are physically fixed, which is the substrate in the film. So if I have a substrate film that's really, really tight, no porosity or anything, and I change the potential, I mean, in theory, you could have some effect there if you, I don't know, overly oxidize or reduce or something to your film or your polymer or whatever. But for the most part, that's physical. That's relatively unaffected. But you are going to change the Faradaic reactions that are happening at your electrolyte. That's where, at your film or at your substrate even, or the amount of double layer capacitance could change because it's a liquid, liquid solid interface. So oftentimes by changing the potential, you can sometimes elucidate whether that's the case. Now, the other way to tell is whether you have microscopy, right? Or some kind of in situ or ex situ kind of analysis of your metal in your polymer. If you're able to do something like that, you might be able to tell whether part of your substrate film has porosity, anything like that to it or not. Okay, and in the case that you can determine that, you might be able to successfully figure out which of those models is most appropriate. Okay, it looks like there's a series of questions. I'm going to try to look through this and see what I can do with this. So Techi has asked, again, quite a general question about learning the concepts of electrochemistry. And that is all that they have asked. So I'm going to move on because, as I said, I appreciate the comedy. If Rashid has asked, "What is electrochemistry?" I'm not sure if you're trying to be funny. If so, I do appreciate it. One of the things I said at the beginning of the live stream, perhaps if you're with me, was questions like "What is electrochemistry?" Are often there. Just what is EIS are quite broad and a little too general for me to answer in a short time. So while I appreciate the interaction, I will try to move to questions that are able to be answered in a reasonable time and not too broad and not too overly specific. Perhaps I hope that makes sense. Let's see. Let's see if I can take this. Looks like Rasmi has a question. I think this is same person who asked the previous question. I think so. Yes. So during hydrogen permeation experiment of a steel membrane, why a corrosive layer is formed on the hydrogen charging side. It is supposed to not be formed during cathodic charging. So in a hydrogen permeation experiment, if I'm not mistaken, I think on the hydrogen charging side, I'll try to pull this up while I'm talking, but I don't want to have like dead time if I can avoid it. So you're not just staring at me, staring at my computer. Corrosion. To the best of my knowledge, on the hydrogen, what is it? Sorry, hydrogen charging side of the metal or whatever. You often will put a coating. I don't know exactly how, if it's done electrochemically or physically, but a lot of times these procedures involve putting a layer. There's an ASTM thing. I'm trying to pull it up if I can. Hydrogen permeation. A lot of times, again, to avoid that here. So like a palladium, like a noble metal. Okay. So this is a very quick, again, without taking forever to answer your question. And I would encourage you to look into this a little bit, perhaps in the literature. But here's one example, one paper that talks about, I'm not sure if this is 100% related to what you are asking, but I think it's a similar kind of a phenomenon. So you'll see researchers apply a palladium coating on top of either the entry or the exit. So I think that's an answer or the answer, to be honest. To avoid this kind of corrosion that happens is you have like your metal. Sorry, let me stop sharing. Get back to PowerPoint. So very, very loosely, and I'm not an expert in hydrogen permeation, to be clear. I do know a little bit about it, but essentially it's like you have a metal disc, right? And you have solution on this side of it and you have solution on this side of it, right? Very, very, very briefly, very roughly. Okay. And so I have solution on this side, I have solution on this side. And on one side of it, you're producing like hydrogen gas, and then you're trying to see if it permeates through and detecting it on this side if it made it through or something to that nature. And so the generation of hydrogen on one side, you people will put a coating of noble metal or whatever to protect the surface from corrosion itself. Something like that. It also can help generate hydrogen because it's a better catalyst. So I think that's what people are doing, and why it's corrosion is happening is because hydrogen. Hydrogen, I think this is part of the issue. Is it can be corrosive to the metal during its its usage. Again, I don't know if I can speak too much more to it because I'm not great of an expert on this. And again, I have a handful of papers and resources, but I'm not going to dig through them live with you, and I don't want to kind of waste your time, I suppose. But I would look into that and read about those films, like noble metal films. Sometimes it's like silver, things like that. So not totally noble metal, but that people will put onto the surface to try to avoid that type of problem. Okay, let's see here. Question about Tafel slope, my favorite. Let's see. So this says from Mahesh, what is the importance of Tafel slope? What are different methods to find it for electrocatalyst? What is the impact of Nafion on LSV, CV, and impedance of the catalyst? So I showed this just a few minutes ago. I'll bring it back up just for good measure to answer your question. What do I got here? Let me share the presentation for the RRDE again. I have like 5 PowerPoint presentations open now. Here it is. Okay. So the Tafel slope, what its importance. So generally speaking, it gives you kinetic information without giving too much, taking forever to answer this question because it is the topic of this. For example, I gave a webinar and talked about it for like an hour. But very briefly, the Tafel analysis comes from the Butler-Volmer equation, which is an equation that describes the kinetics of an electrochemical half reaction. And so the kinetics of a reaction are the Tafel equation, and then Tafel slope comes from that. And so the importance of the Tafel equation is that it gives you, or the Tafel slope, I should say, is that it gives you direct insight into the kinetics of whatever you're studying. Now, again, as I mentioned before, built into that is the assumption that you must be looking at kinetic information, which is to say kinetic current, and not just any current collected on your electrocatalyst. But if you're able to do that, you can primarily get things like the Tafel slope, which is changes depending on the alpha, the symmetry factor, which is often just 0.5, but and changes based on the temperature. You can see how the temperature changes the kinetics by looking at how the Tafel slope changes. And then N, that number of electrons. As I said, I had a whole discussion about this just 20, 30 minutes ago about kind of assumes that it's 1 electron. So in theory, you should always have 120 millivolts per decade. But, the short answer is that you can get the difference of Tafel slope indicative of multiple electron transfers. So you can get you can say, oh, there's 2 electrons being transferred. There's 3 electrons being transferred. The longer answer is something to the effect of go read the literature on Tafel analysis. It's quite comprehensive, right? I can't really do it justice in a very short amount of time, but hopefully that's a brief overview. The Tafel equation and Tafel slope comes directly from the Butler-Volmer equation, which is a fundamental equation that studies the kinetics. And so the importance of it is that you're getting insight into the kinetic processes of your electrochemistry, the reaction that's happening. The next part of your question was about Nafion. What are different methods to find it? Yes. So the methods for finding it. I mean, any way where you have the ability to get purely kinetic information. So, rotating electrodes, for example, as was what I was just showing you the slides of. I did my webinar last year on this. When you rotate the electrode, you can extract using the Levich analysis, the mass transport and kinetic currents. And so you can isolate kinetic information, kinetic current, when you are able to rotate, control the diffusion layer thickness, and extract that kinetic current. And so that's probably the most popular, I would guess, method for doing that. The other is to simply assume in some situations that the bulk of your current is the result of kinetic processes. It's not always exactly the case. It's a dangerous assumption because there's non-Faraday processes. There's other diffusional things going on often. So the number of milliamps or amps or whatever microamps you get, to assume that that's all kinetic current can be a dangerous assumption, but it is technically possible to make Tafel analysis. If you don't have the ability to rotate your electrode, if you take current in a place where it's mostly kinetic processes occurring, it is perhaps reasonable to then use something like CV or bulk electrolysis or something as a method to find the Tafel slope or do a Tafel analysis. And the last part of your question was the impact of Nafion on LSV, CV, and impedance measurement. I guess I don't know exactly how to answer that. I'll be honest. Nafion is probably the most popular membrane in the world, or at least in electrochemistry. I should say that because there's certainly a lot of membranes out there. There's a lot of, non-electrochemistry experiments where membranes are used, but Nafion is probably the most popular electrochemical membrane. It's used primarily for proton exchange devices, fuel cells, electrolyzers, things like that. What is its impact? I mean, Nafion is a separator, right? It is ionically conducting and not electrically conducting, so that it separates two electrodes electrically, so you don't short the cell, but ions pass through to complete charge balance, and so that's why it's really useful. It's stable. It's relatively inexpensive at this point in time. Maybe it wasn't always. I don't know historically how expensive it used to be, but it's relatively accessible. It's relatively cheap. It's pretty stable. It's like shelf stable. It's safe to, it's not really toxic to my knowledge. I mean, I wouldn't recommend touching it with your bare hands or eating it, but Nafion is pretty ubiquitous and used for some of those reasons. But what its impact, I mean, so I guess I don't exactly know how to answer the question, to be perfectly honest. Like, impact compared to what? Like it's just a necessary component if you're doing a separated kind of a cell or a fuel cell, right? You have to separate the anode and the cathode, or working in counter electrode or something like that. And so it's just a separator. Or like I was talking about before, and this is the last thing I'll say about it, and then I will move on, is Nafion comes as a liquid suspension, like it's like a solution, and it can act like a glue for your thin film. If you're doing like a thin film on a glassy carbon disc or something of that nature, it glues, and it can help facilitate the transfer of protons, positively charged ions in solution, to the electrode, or to the film that you've made. beyond that, I guess, yeah, that feels somewhat general. Like, what is the impact? I mean, yeah, again, I guess that's the best that I can kind of answer that question. I hope that's a good answer for you. If you have a follow up, you can type it, and I will certainly try to answer it if I can. Let's see here. See, there's a lot of questions. Some of them say, "What is electrochemistry?" And I'm going to ignore them. It is certainly the case that the internet will do internet things. I'm not. I wasn't born yesterday. Okay, let's see. There's a couple of questions by Ironic TV. Let me try to get through this if I can. Let's see. And bear in mind that again, I'm desperately missing my colleague Alex, because one of the things that's really nice about these live streams that we do is that, like, while I'm answering a question, Alex is looking at the chat and like thinking about the next question to answer, and sometimes we can kind of like think about it through, and vice versa. When he's answering a question, I will be looking and trying to like pick up the resources and answer it. So you get me answering on the fly. So apologies if I'm working my way through this, trying not to have a bunch of dead air. But as I said, I'm doing my best, and I can't promise that I know absolutely everything. And that being said, let's see. Ironic TV says, considering the cathodic reduction potential under non-standard conditions, okay, and factoring in the dynamic interplay of reaction kinetics, how might the imposition of anodic overpotentials on a redox system modulate the electrochemical intricacies of ion transport? Okay, this looks like you generated this using AI. Conventional Nernstian expectations. Something tells me this was someone put in ask a question about electrochemistry into an AI. And I'm just going to assume that's what happened here, and I'm going to move on. So if it isn't, I do apologize, but this doesn't seem like a question that is being asked for real. And if it is, I apologize, but that's what it strikes me as. Okay. Let's see. Trying to get through these. The other thing Alex does is he cleans up some of the questions that are clearly not asked in earnest. And I'm trying to do that on the fly. So thank you for your contributions, everybody. I appreciate it. If we take acid and react with acid with electricity, what will happen? It will get electrocuted. That is what will happen. You will electrocute the acid. It's a very, very dangerous thing to do. Again, I'm not sure, and I do apologize if this is a question asked for real. I just some of these questions seem like it's internet trolling, which is fine, but I'm not going to stay on these questions for too long. In that case, it's all in good fun. Okay, let's see. Lewis has a question about chronoamperometry. We are using this technique to measure the efficiency of antiscalant substances to be used in cooling towers. So we have solutions of calcium chloride and sodium bicarbonate. And we are reducing dissolved oxygen to hydroxide and precipitating calcium carbonate on the electrode. Why does everyone use RDE instead of RCEs? The flow in heat exchangers is turbulent. So you don't, I guess, so first of all, I don't see why you should have to use RDEs. In fact, in this particular case, you probably should use RCEs because, so to sort of, you probably inherently understand this since you asked the question, but for those who may not understand what these acronyms are or what Lewis is asking about, RDE, rotating disk electrodes, is where you are rotating an electrode with a shroud upside down, and it produces laminar flow pretty much exclusively. I mean, if you rotated insanely fast, it would get turbulent. But basically, you have this disk, right, upside down, and you rotate it like this, and it's in a solution. Make sure you can see this. Yeah. Let me hide that question so you can see. right? Okay, and I have solution, and so as I rotate, I get this this vortex effect flowing up, and then it kind of circulates, right? And the flow right here, right at the disc on the bottom, is laminar. Smoother laminar flow. It's determined by the Reynolds number, but I won't get into that too heavily. On the other hand, the flow here around the outside of the cylinder, that is turbulent. Okay. Now, turbulent flow is used for things like you're describing, Lewis, which is why I guess when you say, when you write, why does everyone use RDE instead of RCEs? I guess my fundamental question is, are there folks in doing your type of, efficiency of antiscalant substances in cooling towers? Are they doing mostly RDE? Or are you just sort of speaking generally about why people do RDE? Like, generally speaking, generally why people do RDE is because laminar flow is easy to characterize with those equations I was talking about and things of that nature. But RCE, rotating cylinder electrode, where basically instead of your electrode being this disc at the bottom, your electrode is now instead a cylinder. It's like a slice of this, right? And so the surface of this cylinder as it rotates is exposed to turbulent conditions. And then that's actually a whole field of studying rotating cylinder electrodes for turbulent flow. So okay, I see you've followed up a little bit. I'm gonna try to come with you here. So hydroxide with bicarbonate gives water and carbonate. Yeah, that's like an equilibrium reaction, I think, right? So we have a local increase in carbonate concentrations and precipitation of calcium carbonate. Okay. Is it because turbulent flow would not allow local increase in carbonate concentration and therefore not lead to precipitation? Turbulent flow would not allow local increase in carbonate. I don't know that that's true. Why would turbulent flow not do that? It's, turbulent flow is more like, right, what are the differences between turbulent flow? Like, it's more chaotic and everything, but it's got better mixing. It's probably going to lead to, everyone in scientific literature uses RDE. I'm guessing they're trying to study the kinetics of it or whatever. Like, the equations for RDE are pretty well established and known. I mean, the equations for a rotating cylinder electrode are also, I'm trying to pull one up if I can, like the Eisenberg equation. I think that's, you can study rotating cylinder electrochemistry that way. You can get some information. I just think that perhaps the answer, if I had to get, like, I don't know exactly the field intimately that you're talking about, right? Like, so I can only kind of speculate. But generally I would say that it might just have to do with the fact that that the laminar and RDE kind of experiments are like easier, more well known, well characterized with the sort of switching mass transport and kinetic information pretty nicely. Turbulent flow is perhaps more empirical. For example, I'll, as a somewhat shameless plug, I suppose, but it's just the easiest thing I have to kind of illustrate. We have a web page on mass transport limited corrosion on our website. And so, there's a lot of empirical, like the relationships, like I think this is the Eisenberg equation. I think this one. Yeah. So it just becomes more empirical, right? You have Reynolds number, this is what the Scantle number, the Schmidt number, excuse me. And so you end up with things like diffusion coefficient, what the Sherwood number, and a lot of times these are more like physical properties of your solution, right? Maybe it's that you're not getting as much kinetic information, something of that nature. I'm just kind of spitballing here a little bit, but I would encourage you, if you sort of have this knowledge, like, and it's one of the reasons why people who are studying corrosion in pipelines, for example, which is analogous to what you're doing, it's not exactly the same, right? But the whole like antiscalant substances, that's similar to corrosion inhibition, right? um, Corrosion inhibitors in like oil and gas pipelines. It's not exactly anti-scalant. It's similar, and there's this whole. I'll just touch on it briefly because I know a little about it, but there's a whole thing about like the formation of carbonates is actually inhibiting. It's its own sort of form of inhibition of future corrosion, but it's bad because carbonates are brittle. Eventually, they'll flake off, but in the moment, they actually serve as an inhibition. So it's kind of a weird double-edged sword. But all of that is discussed and studied with turbulent flow with cylinder electrodes, because the flow in pipelines, and probably I'm guessing in your coolant tower is also turbulent. As you say, yeah, the flow in heat exchangers is turbulent. So I would encourage you to consider both. Maybe if you do some cylinder electrode experiments, you'll find that you can't get the parameters you're after. Maybe you can't find the, I don't know, proper like kinetic parameters that are comparative to what people are doing with RDE. That might be part of it. But I would say you can do things with cylinder electrodes, RCEs, for example, to correlate with respect to pipeline flow. And that's what a heat exchanger is. I mean, it's basically flow through pipes. You can probably do this. Correlate the rotation speed of the cylinder to the turbulent Reynolds number, the flow. You can correlate that, and then you can get the right viscosity fluid, and you can kind of create an analogous situation without needing flow. It's a batch process, right? It's RCE is a batch process. You might be able to do some experiments. And if you're wondering why everybody does a thing and they're not doing this thing, well, maybe you're the person that needs to suggest that they should do this different thing. Maybe the innovator is you, because this is a good question. I think you're thinking the right way, so to speak, which is that you're looking at this and saying that probably makes more sense. So yeah. So I hope that's, I don't know, a moderately reasonable, I don't know, extrapolation of this concept. And I like the way you're considering it. I hope that you do find something kind of interesting if you go down that route. Let's see. Splash has asked, how did the van der Waals forces work? Van der Waals forces are like loose attractive. This isn't, I'm not sure this is exactly electrochemistry. It's more like chemistry, but I think the way I always thought about van der Waals forces was similar to like gravity or gravitational pull, but in a molecule state. So like if you think about like planets orbiting around each other, that occurs because of centripetal force. There's a the force of gravity, right? You can look up the equation. It's like it involves the masses of the two things and the distance to over the distance squared or cubed or something. I'm butchering this because this has been like physics class from high school, but basically it's like attractive forces based on their mass, essentially their size, compared to like actual like chemistry, like covalent bonding or ionic bonding or something like that. Van der Waals forces are kind of like just the attractive forces that occur from molecules just physically being near each other. But it's let's see if I don't know if I can get a, you might do yourself some service by finding a textbook, like a general chemistry textbook, and finding a better explanation than that. But that's the I don't know, the general overview that I always imagine. It's just sort of this relatively weak, attractive force that occurs just between molecules, just their physical size, sort of something like that. And it's not like strong binding thing, but I tend to think of it as similar in a way where like molecularly or on a a small scale, like van der Waals attractions and forces cause molecules to like get in the way. Like they're like physically in the way. Like I'm trying to get my reagent to make it to the surface, and this other particle's like blocking it because there's van der Waals forces. And I don't know. Think of it like pool balls on a table, kind of getting in each other's way. Something like that. I don't know if that's accurate enough or whatever. That's kind of always how I've I don't know, envisioned it or something like that. Let's see. Enoch says, again, this is a bit of a general thing, so I don't know that I can exactly help you in this setting, but need some training on a metal air battery, specifically ORR and OER. Yeah, I mean, this is again sort of one of these things. It's a little too broad and general, for me to give you advice, now like this. So I am sorry if I can't, I don't know, do a lot more for you now. Batteries are, I haven't worked with metal air batteries either. So to be honest, it's not my expertise. I've worked with lithium ion batteries. It takes practice, and I know that I'm sort of punting the question to an extent because like I can only do so much for you on a live stream like this, or in a very general way. I can't give a 10-minute comprehensive lecture on how to do a battery test. It's quite a, there's a big research that people spend. I spent 3 years of a PhD doing this. But what I will say is that it just takes a lot of practice, and it takes someone. Hopefully you can have someone who can like stand with you in the laboratory and show you a few little tricks of the trade. Because like when you're making batteries and when you're the data analysis, you can sort of learn electronically. It's like I could show you how to do like battery data analysis, for example, like without being physically with you. But someone is going to have to, if you're like doing research and constructing batteries, there's a lot of just tricks of the trade that you'll end up having to learn. Same with like making fuel cells, with almost anything else, right? You end up learning all of the little things as you go. And that's frustrating because I know that you sometimes feel like, how am I supposed to learn all this? Or it's a lot to learn or what have you. So I am sympathetic to that, but unfortunately I can't be sort of a comprehensive, help in that regard right now, I suppose. Let's see. Salah has a question. How to do IV curve test for pressure sensor. The sensor is attached to an electrode. The test under different pressure load. Can we use CV to conduct such a test? You can certainly do electrochemistry under pressure. How do I do IV curve test for pressure sensor? So, pressure sensor. I guess I don't totally understand if the sensor's attached to an electrode. Are you trying to correlate something? Like, are you trying to measure the pressure with like correlate electrochemical results with the pressure? Or are you just trying to do electrochemistry at different pressures and like see how it works? I guess I don't know if I totally understand the context of your question, so I do apologize for that. I guess what I can try to say generally is that absolutely you can do electrochemistry under a variety of different conditions: high temperature, low temperature, high pressures, room temperature, room atmospheric pressure, or whatever. You can certainly do things like that. How to an IV curve? I mean, you can do CV. You can also construct an IV curve or like a polarization curve. For example, sorry, I see a follow-up. When the load increase, the resistance decrease, and the current increase. When the load increase, resistance decrease, and the current increases. Yeah, that makes sense. Like if it's like I don't guess if it's like a fuel cell or something. I guess it sounds like you have some sort of like high pressure fuel cell or kind of piezo resistive sensor. Okay, so I'm not great knowledgeable about this. What I will say, I suppose, and maybe this is helpful as far as like constructing an IV curve, which again might be called like something like a polarization curve. Let me sort of try to draw a quick thing for you. I don't know if this will be exactly related to what you're asking. So if it isn't, apologies, but I think it's decent kind of advice. So if you're getting a polarization curve for you have a piezoelectric sensor, whatever you're sort of doing, your polarization curve is something like you have your open circuit sort of voltage, and then under load you reduce the voltage and you start to get current. So my current is going out higher, and then eventually you might hit a plateau or something as the voltages drop. That's like increasing load, right? That's my load as I drop the voltage, let's say. And this is like increasing the current. And as the current increases, the resistance, they're hand in hand, right? If you think of Ohm's law, right? V is IR. In some general sense, as resistance goes down, current goes up. They're inversely related. So that's not surprising. To get a curve like this, though, is what I was going to say, is that you can do CV, you can do LSV, which is to say you can just take your voltage, E0 is 1 volt, and then scan at, 10 millivolts per second to, 0.01 volts or whatever. So that's like one way to do it, a CV or LSV, to get a polarization curve. Another way to do it, though, is a series of, and for your case, maybe I'm just sort of hypothesizing here, maybe this is a better way to do it because you have like high pressure. Maybe you have, I don't know, some degree of like giving it more stability will help it, like for relaxing, something like that, because high pressure is probably hard, a little bit tricky to deal with. You can do a series of chronoamperometry. So instead of this is like LSV approach to polarization curve. Instead, what you can do is apply a bunch of potential steps and let them sit there for a while. How often you do that is up to you, but you could do like, E1 equals 1 volt for, I don't know, 15 seconds. E2 is 0.98 volts for 15 seconds. E3 is 0.96 volts for 15 seconds. You get the idea, right? So then you're just going to drop by 20 millivolts or 10 millivolts or 5 or 1 millivolt. You could do a lot of them. And it's like what you have instead there is you have a series of steps. If you imagine time versus voltage and current, you're creating your polarization curve, but in a little more of a stepwise and also stable way. So your voltage is like for a little while and then drop it by a little bit. You're doing a staircase, an extended staircase, instead of a sweep. And so the current that you get is allowed to like stabilize at each of these. So the current here will be like nice and stable, and then nice and stable, and then nice and stable at the end. So like it compared to where whatever these values will be, you see, you get this sort of like decay curve is like a Cottrell equation basically. Whereas like if you sweep, you're getting like closer to here, like the top of, it's like it's constantly unrelaxed or something of that nature, something like that. Whereas if you let it sit at each potential for a little while longer, you sort of construct your polarization curve in a more piecewise fashion. But you could think of it as a little more accurate. Some people get their polarization curves that way. So I just wanted to throw that out there. It's a different way to get an IV curve or a polarization curve. In my opinion, it is better. It's a little more accurate because it's like the operation of a device. And I don't know if it's your piezo resistive sensor, your device is exactly the same, but a lot of times the operation of like a fuel cell or an electrolytic cell or something like that is that you're setting a particular power or voltage, current, whatever, and you're setting it there. So it does settle out. So if you're trying to find what the polarization curve representative of your system is, it should be like sitting at a potential so that the transients are gone and you have like your steady state current. So that approach is probably a decently good idea in my opinion. Okay, so train ZZ123 has said, what are the working principles of a lithium sulfur battery? Slightly confused how they differ from lithium ion batteries. So what's interesting is that, well, first of all, I don't have personal experience testing lithium sulfur batteries. I do know lithium ion batteries pretty well. All I can really tell you is with my limited knowledge of lithium sulfur batteries, the working principles of them are significantly different in that lithium sulfur has like a bajillion oxidation states. It's like when you look at like lithium ion batteries, like the anode is graphite, and it's like LiC6. So you have like a sp2 hybridized carbon or something like that, and it's just lithium intercalates into it, and you'll have like like one lithium to 6 carbons basically, and it's like if it's just Li like X C6, where if X is 1, it's fully charged, like a full mole of lithium per 6 moles of carbon, essentially, or like carbon ring, something like that. You could think of it that way. But it's pretty like standard. It's not like a million oxidation states. Whereas lithium sulfur, and I'd have to look it up again, and I'm not like overly familiar with it, but the process or the procedure, the mechanism or whatever, it's like it's crazy. I've looked at it in the past, seen some papers on it here or there in my time, and it's just like Li2S12, and then it goes to Li4S19. It's wild. So it's sulfur is one of those elements that has a lot of crazy oxidation states and compounds that a lot of like really cool and wonky binding and things like that. So I think that lithium sulfur battery offers the promise of like really high. I think I don't know enough really firmly of their application. Lithium sulfur battery, I think they're more toxic. Sulfur is obviously a little more toxic of just a element, and sulfur compounds can be dangerous. So some of that I think plays a role as far as its safety and toxicity and things like that. I think it's one of those that perhaps has maybe in some cases it has a higher theoretical capacity or power density or something like that. I don't know for positive. But as far as the working principles, I don't know the mechanism or the chemistry. That's probably the most that I can say with relative certainty from what I have seen or know just offhand without doing a little more research myself on it, to be honest, is that it's just there's like a billion mechanistic steps and oxidation states, and it's crazy. Lithium ion batteries are relatively complex as well. It depends on what your anode and cathode is, of course, but in my I don't know, somewhat casual observation, it seems like lithium ion batteries are a little less complicated as far as the mechanism and the oxidation states or whatever else is going on. or so at least it appears to me. So that's I think that's about as much as I can say about lithium sulfur batteries with relative intelligence. I say relative because I guess it's not something that I'm the most well versed in, unfortunately. So I don't want to give you too much information if I'm not totally sure. I might be wrong, you know. But yeah, I would encourage you to read up on lithium sulfur batteries. Also, I might do the same, because now you've kind of got me thinking about it and trying to get myself a little more knowledge of how they work in comparison to, things like lithium ion. And I never did. I never used, like I said, never studied them. And I don't know. I always felt like when I was in graduate school, I had this like, or as a postdoc, like I had a real hesitancy of like wanting to work with chemicals that are like, or that are really just really hazardous and toxic. It's like I'm a chemist who's afraid of chemicals. It's like, it's not a good look. It's not a good idea. Like I never thankfully had the need or the chance to work with hydrofluoric acid. Still to this day, it's one of those chemicals that scares me to death. Because you learn about what hydrofluoric acid can do, like it seeps into your bones and like dissolves the marrow or something, and like you don't even know it's happening because it doesn't hurt until later. And it's like, that's so terrifying. Like I would just rather not get a PhD than work with hydrofluoric acid. I know plenty of people do, and maybe you sort of take the proper safety precautions and it's just fine. I know people work with hydrofluoric acid all the time, but for some reason, when I think about lithium sulfur batteries, some of that kind of stuff comes to mind, because sulfur, like hydrogen sulfide, is really, really toxic and dangerous. People also use that for some kinds of, corrosion studies, actually. But the idea of testing with things like lithium sulfur battery kind of like freaks me out a little bit, because sulfur's so toxic. And yeah, I don't know. I like to make sure I have the same number of fingers and toes with me when I went to work as when I get home, and I like to make sure I have roughly the same number of brain cells, and I'm not developing any conditions because of my research life. Some of that stuff was always a little bit a little bit freaky if you're in a research lab. I hope all of you out there are safe when you're doing your research, and wear all the proper PPE and everything. I know that I feel like the laboratories now are better at that than and I'm not that old, but I'm old enough to know that when I was in school or in other places, like it's not that we weren't safe, but there were definitely some situations where like people weren't all that caring. Like, whatever, just go get some work done, and I my feeling, I'm not trying to impugn anybody, I'm just saying my feeling was more like, it's not that safety wasn't a thing, but it was just more, it wasn't as emphasized. I feel like now more so, as I'll visit people's laboratories, I'll travel and visit customers or whatever, and it's like there's way more like intentional safety protocols, and I mean, honestly, it's probably for the better. Like it's obviously better to have people be safe, especially when doing research with lots of complex equipment and dangerous chemicals and stuff. But there is something to the idea of just getting stuff done quickly and not caring about whether it's safe or not. Sometimes it makes it faster, but yeah, I guess ultimately it's not a good idea. I guess I should be grateful I didn't get ever severely injured while I was doing research, because I have a tendency to also have that sort of attitude sometimes. I'm just like, this is like I'm an engineer, so I just have this like, this will be quicker. I'll just do it this way instead of like sometimes like take the time and do it right. Like that's the way it should be done. Anyway, kind of going off on a bit of a tangent on dangerous chemicals, but I think what I'm going to do is call it a day. Unless there are any questions in the last minute here, I'll just I'll give it another minute or so. But while I do that, I guess I'll just say thank you, everybody. I hope this was helpful. I hope that I hope I was able to answer anybody's questions. Let's see. Oh, so I do see a follow up here. Yeah, it looks like another thing about lithium sulfur. Again, I'm not sure how much more I can pontificate on this. Do I know about the charge, how charge discharge works in lithium sulfur? Yeah, like again, it's let me see. Let me just see if I can find something like really quickly. It's so it gets really crazy. Like here, did you do a quick search? I'll just kind of show you this just to prove my point and possibly to prove how little I know about it because I'm not above embarrassing myself. Like here's like if you just search lithium sulfur, it's not getting. Why isn't the picture getting bigger? Hang on. Like I know it's a little small to see, but like this is you see like all this cascading down the side is if that's showing up there. I know it's really small, so but this is like S8 plus 2 lithium gives you Li2S8, and then it's Li2S4, Li2S3, Li2S2, Li2S. Like it just there's so much there. So I guess very possibly the answer or an answer to that question is something like it's an ever increasing or decreasing depending on charge or discharge intercalation of sulfur into the lithium, something like that, and the oxidation state it changes depending on how much is there because it's it's different compounds entirely. So but ultimately I guess I don't know if it's an intercalation and technically intercalation reaction. Usually an intercalation reaction is where something joins, like that's what the lithium carbon anode reaction is. It's called intercalation. Like lithium is entering the lattice, intercalating, joining the lattice of another material, whether it's carbon or whatever other anode you're working with. Sometimes it's like a decomposition reaction where it actually changes, like it's like a actual chemical reaction where something is decomposing into something else. So some of the answer to that might be along those lines, like specifically what kind of like how the discharge works, like what kind of reaction exactly it is. If that's technically it seems like it's an intercalation, like an ever increasing or decreasing intercalation of sulfur into a lithium sulfur lattice, and as a result, the oxidation state and physical structure of the LIS cathode is just constantly changing in interesting ways, something like that. But again, that's probably the most that I can easily answer that question because as I said, I don't have a lot of other knowledge of lithium sulfur batteries apart from some of these sort of general observations about it being pretty crazy, I guess. Dooley says, is there a place that lists the questions asked so far? I guess I think you're on YouTube. I suppose if you, again, maybe if you just joined or something, I'm not sure how. YouTube is strange with this. Sometimes if you join, you should be able to scroll up in the chat and see the questions previously. But if you're asking about like the questions that were answered, everything that I'm saying now and the transcript and the recording of this event is going to exist on YouTube permanently in our YouTube channel, which is where you are now if you're watching me. And the folder, whatever this is in, to ask us anything about electrochemistry, because I guess this is episode, I don't know, 34 5 at this point or something like that. We put the timestamps in the description. So from previous weeks. Yeah. So all of the ask us anything about electrochemistry. Oh, you want like a full master list? I mean, we could probably do that. Honestly, that's interesting. It's an interesting concept. Like at some point, I suppose I'll think about this. If there's a way to do this that makes sense or is worthwhile, I don't want to, because like if you take like all 30 whatever of these, ask us anything about electrochemistry we've done on YouTube in the, like what the description of the video itself is our timestamps, and we, Alex or I will add those to, put, oh, well, here's where at 21 minutes and 15 seconds is when someone asked about, the Tafel equation, and that's when we answered that. So it's like we can have easily copy and paste all. I mean, you could do that too, obviously, if you like, but some sort of just aggregate of all of the timestamps and the questions there. Maybe we'll think about something like, I don't know where we would put it, to be honest, maybe on our social or somewhere in the YouTube channel, like a post of some kind. I'll have to think about it, like a list of all the questions that have been asked. I guess I would say 2 things about that in closing for this, I suppose, because I'm going to wrap this up now. The first is that could be nice, because if someone, at any point has a question about whatever, something we've answered before or we've talked about, they might be able to just say, oh, I'll go to the master list, and that's in episode 21 at 19 minutes. So they can just find it that way. I think that would be a cool resource to do, actually. So I am going to make a note of that. Thank you, Doolies. I kind of like that idea. On the other hand, what I will say is that there's something to the idea of hearing it live over, and like, even if you can listen to a recording of it, like that's why I like that we have this live stream. We do this every week, and the recordings are there. To your point, like look up a question that was asked. But sometimes I just think that, there's really no substitute to, like, and I've just found this experientially, like I do webinars, and some people have come to my webinar like on the same topic, separated by 6 or 12 months. And and people have, I get feedback where some folks really enjoy that. Even though they can watch the recording, they'd rather hear me talk about it live. It's like, it's like class, right? Or live instruction. I think that there's always value to that, right? Rather than just, like there's levels, right? Like you can read it in a textbook, you can watch a video, or you can have someone tell you live. And I think that I bet if we make this master list, there's so much overlap. There's probably going to be a lot of similar questions, probably worded slightly differently or asked slightly differently, but there's almost there's never an end to the amount of times that Alex and I get questions about what is this aspect of impedance, or why does my resistance look like this, or what something about the Tafel slope, or the RDE. Like these questions are forever, and part of that too is because there's always new students coming into graduate school, and when you come into school, you need to learn all the things, and there's always new students who need to learn stuff. So I like that we sort of have both, I guess, to your point, right? Is that we have, this list of, in this archive of these live streams with questions categorized, and a master list is a cool idea. But I also like that hopefully we keep showing up. If people keep coming and watching us, we're going to keep doing this. And if it's helpful for people, and, to hear someone talk about it live is a little different, and answering your question directly, can be a little different and a little bit more helpful, I think, in some case. I know I felt that way. I had a really great advisor when I was in graduate school, so that helped me. Like if I had a question, he would answer it. He would help me. And hearing it live rather than watching a recording that he had made, or reading it in a book, hit home a little easier, and probably helped learning it a little more deeply, or something like that. So anyway, yeah, I appreciate that. I am going to make a note of the master list. It's kind of a cool idea. We'll see if it's something worth doing and exactly how we implement it. I'm not sure about those details yet. Ahmad wants to know what it takes for a synthetic organic chemist to master electrochemistry principles. Practice, my friend. Practice and time. Just like any other discipline, you know, just like any other thing. Get your hand on some get your hands on some equipment and some electrodes. Get a potentiostat. Just do it. Do it. I mean, yeah, you can read textbooks. You can come here and listen to me talk for several hours if you want to. I'm not sure I recommend that, but I appreciate it nonetheless. Really, honestly, it's just practice. I mean, one of the fun things, and I guess I'm going to say this in closing, and then I will definitely leave you all there. One of the things that has been fun, in particular for me, in doing this Ask Us Anything about electrochemistry has been how many folks that I've talked to and sort of met casually, electronically, I suppose, people that are interested in electrochemistry or doing electrochemistry, but aren't even necessarily graduate students. Like, that blows my mind. Like, I always have had an interest in batteries. Like, that's partly why I really shifted my PhD that way, and I did my postdoc there. And I really have an interest in batteries. It's just something about them always, I don't know, I always felt was cool. Like when I was a kid and in high school even. So it was cool to like get to school and get to learn about them and study them and research them and everything. But it like would probably have ever crossed my mind to like study electrochemistry outside of a university. And so I'm fascinated and also like deeply impressed by any of you who are, outside of the envelope of academia or industry or anything, and you're just like chugging away doing electrochemistry or in any capacity. I'm deeply impressed and in awe of you, and it's cool to see, because we're a relatively small niche industry in science, and electrochemistry is really useful and ubiquitous. Everybody's walking around with a phone that uses electrochemistry, but not a lot of people know about it comparatively, I think. So anyway, I hope that was enlightening for you as it was for me. But I hope I answered everybody's questions relatively well enough. It's tough without my trusty sidekick here. Hopefully he'll be back next week. But in any case, I do appreciate everybody joining me this week for Ask Us Anything About Electrochemistry. I hope everybody has a great, happy new year and has a great, prosperous 2024. And we will see you all next week. And thank you again.